All right. Thanks, DJ. So today we're going to be focusing on VRV piping from a design and application perspective. So what I mean by that is I'm going to try and stay away from the installation side of things. So we're not going to be talking about like brazing practices or pressure testing or anything like that. I'm going to focus primarily on the design and application, and I'll talk more to what I mean by that here in a second. So before I get into things, I just want to introduce the applications engineering team for those of you who haven't had the opportunity to meet any of us or all of us. So we work out of Houston. We're led up by Robert Powell, the applications engineering manager. There's two other members on the team, Nick and Chris, and then myself. Once again, my name's Sean Turner. I'm an applications engineer. I've been with Lycan for about 2.5 years. And you'll see that we all kind of lean towards a certain topic just based off of our background. I came from the water side, used to be a hydronics applications engineer, so I tend to support the water-cooled product quite a bit. Chris is a good source for outside air, and then Nick does a lot of competitor comparison type stuff. But we all do support all of Lycan branded products. So a big portion of that is VRV, hence why today I'm talking to you about VRV piping practices. So how I'm going to break things down today, as always, we're going to start out pretty basic. I'm just going to first introduce the type of piping, different type of components in the system, and then sizing, why piping is sized a certain way, why it's important, that sort of stuff. And then we'll move on to constraints and optimized layouts. So we'll talk about some of the overall limits that are in place, and then finish that up with how do you lay out the systems to get optimal performance and optimal upfront cost. Then we'll take a look at oil trapping. So what is an oil trap? What is not an oil trap? Why oil traps are needed in some areas and not needed in some areas. So we'll take a look at that. And then we'll finish things up with thermal expansion and insulation. So those two topics are kind of related just because they both have to do with refrigerant temperature. So we'll go through those and talk about how to design for both those. So starting off, the type of piping that we have in these systems, I should really be calling it tubing. The type of tubing because it's copper tube, ACR, air conditioning, refrigeration, annealed or drawn copper. I'm not going to go through each and every material property there. The copper tube handbook is going to be a far better, more detailed resource for that. But just keep in mind ACR, annealed or drawn copper is what we allow in the systems. So what's the difference between drawn and hard? Drawn and annealed. Drawn is hard, annealed is soft. What gets chosen in the application is really dependent on the installer, and it depends on the particular application and what works best for them. Drawn is going to be rigid, requires fittings to go around bends and obstacles, but it does have a higher allowable working pressure. So some of the more conservative contractors are likely going to lean more towards drawn copper. It's a little harder to work with, but you do get the higher working pressures, the additional safety factor. Annealed, that's easier to work with, formable. You can have long radius smooth bends around contours and corners that doesn't require fittings, but again, it's not going to have as high allowable working pressure as drawn copper does. And then as far as the connections out in the system, you'll see flared connections and brazed connections in a VRV system. So the flared connections, most of the indoor units will have flared connections, and the brazed connections, you'll see those on the outdoor units, ref nets, branch selector boxes. And that's one of the advantages of flared connections is they don't require a flame, right? So there's some applications where it's just not practical or not optional to have a flame in that space. And then as far as the actual components in the system, so obviously we have heat pump and heat recovery systems, right? The different components in the refrigerant network, starting at the right-hand side there, the outdoor unit multi-connection kit. Those are essentially just Y joints between the outdoor units. I like to refer to those as a different name as the other Y joints out in the system, just because they have a little bit different installation requirements. So it's important to distinguish those, but essentially outdoor units are connected by these outdoor unit multi-connection kits, and then the main pipe is going to be the pipe in between that connection kit and the first ref net. If it's just a single module system, it'd be that pipe between the outdoor unit and the first ref net. And it's important to distinguish the main pipe too, because it's sized a little bit differently than the other stuff out in the system. So the main pipe is sized based off of the outdoor unit capacity, and you'll see how the other stuff is sized here in a second. Now, moving on, we have ref nets. So those are the wide joints out in the system. We have intermediate pipes. So an intermediate pipe is basically any pipe that's not connected to an indoor inlet would be classified as an intermediate pipe. And then we also have ref net headers and branch selector boxes. So branch selector boxes in multi-port and single port in heat recovery systems. And then really the only other difference with a heat recovery system is we have that third pipe, high pressure, low pressure, sometimes referred to as a discharge pipe. And that's just going to switch between high and low pressure dependent on whether you're heating down it or cooling down that operation. As far as sizing, so I mentioned earlier, everything on the left-hand side there in that darker box is going to be sized based off of outdoor unit capacity versus everything in that lighter gray box on the right-hand side, that's sized based off of downstream connected capacity. So that applies to ref nets and that applies to the piping. So anything downstream of that ref net or that piping is going to be summed and used to size that particular component, and it gives you an idea of how much refrigerant is going to be flowing through that pipe, right? Now, why is sizing important? So I kind of want to go through why sizing is important, because oftentimes we get asked, maybe a contractor installed the wrong piping, they want to know how critical it is to change out that pipe. My recommendation is always going to be to change the pipe out. It's going to be in the best interest in the long run, but sometimes it's beneficial to understand why that pipe needs to be changed out to the correct pipe size. So I'm going to look at three key system considerations that come into play when we're determining these pipe sizes. So first, looking at reliability. From a reliability perspective, the compressor is the key, the heart of the system that we really want to maintain the life of, the longevity of. And there's two things that can really kill a compressor. Not having enough oil in the compressor, it's just going to tear itself apart, or getting liquid refrigerant in the compressor. And the sizing of the piping is going to influence both of those. So we could have, is going to play a part, and I'll explain a little bit more here in a second, but the piping is going to play a part as far as oil management in the system and refrigerant management in the system. From a performance perspective, piping introduces pressure drop into the system. So pressure drop is going to translate to a capacity D rate and therefore an efficiency D rate. So we want to try and minimize the pressure drop in the system. There's also a modulation piece to it as well. So we have to maintain certain velocities to keep the oil within the system, and we have to do that in high load, and we also have to do that in part load, right? And these are variable speed systems. They can turn down. So the limiting factor there is going to be, can we maintain velocities in those low turn down scenarios? So that comes into play. And then sound is a big piece as well. So if you have really high velocity flow, which is basically too much flow through too small of a pipe, or turbulent flow, that can translate to sound. So the sound is going to play a factor. And then lastly, cost. Cost is probably one of the more driving factors. We want to optimize the cost of these systems. Smaller pipe is going to cost less. It's going to be easier to install. And then smaller pipe also requires less refrigerant, and refrigerant isn't free, right? So that's going to contribute to the cost as well. So really, it's a balancing act between all these. Like the design of anything, you're trying to balance cost between performance, between reliability, and find that sweet spot. What it really breaks down to on the liquid side is we want those pipes large enough to prevent flashing of refrigerant prior to the expansion valve at the indoor unit. So we want them large enough so we don't have too much pressure drop. But we don't want them too small where but we want them small enough to reduce the charge and the piping cost. Smaller pipe costs less, has less refrigerant. So we also have to consider not only the frictional pressure drop, but also the static gains and losses out in the system that we see when we have vertical separations between outdoor units and indoor units. Now we do have some means to account for that, like liquid subcooling in the outdoor unit allows us to tolerate some additional pressure drop. That's why VRV systems are able to get some of those longer line sets. So we do have measures to offset that, but again, it's a balance between reducing pressure drop with a larger pipe, but not increasing the cost and refrigerant to mitigate all those benefits. Switching over to the gas side, we want them large enough to minimize pressure drop. Pressure drop is going to be more critical on the suction side, and that's going to have a capacity/efficiency impact, but we want them small enough to maintain sufficient velocity in the system. If the velocity is too low, if those pipes are too large, oil can accumulate on the system. If it's accumulating in the system, that means it's not in the compressor, right? So we can start to damage the compressor or reduce the life of that compressor. It's even more critical in the vertical risers in the system. We don't have enough velocity, the oil can accumulate in the bottom of those risers. So moving on to constraints and optimized layouts. So these are pretty much all the rules that are applied on the piping side. And before I get into this, I just kind of want to emphasize these are by no means needed to be memorized. This is all automatically applied in WebExpress. It can be beneficial to know in scenarios where maybe you're putting it together a selection, you get an error, you see that you're exceeding one of these rules, and if you understand the rule, understand why it's there, understand what the rule is, it's going to be far easier to make the corrections needed to get that system back within the limitations. So that's the main reason why I'm going through those, but keep in mind, automatically applied, not something you need to memorize. So I did lie just a little bit. The one thing that is not included in WebExpress is going to be any piping between the outer unit modules. So the L1 distances I have labeled there. So there are limitations there, but it's not captured in WebExpress for you. So that's something you'd have to be cognizant of. So there's a total length, actual and equivalent, that's specified in that first row there, the 33 and 43. And then there's a vertical separation between condensing units as well. It tends to be 16 feet. So I won't go through each and every one of these, but we have a limitation as far as the total network length, outer unit to indoor unit, what that farthest distance is, distance after the first RefNet joint, and then we have some various vertical separation distances. And those are gonna vary a little bit based off of whether the outer unit's above the indoor unit or the outer unit's below the indoor units. And then you'll see I have footnotes on a lot of these, where you see we can go to these longer lengths, but there's these additional constraints that apply. And I'll explain that here in a second. The one last thing I want to mention before we move on is the distance from a port to an indoor unit, or basically a joint to an indoor unit. That always has to be kept at 130 feet. So any indoor unit has to be within 130 feet of the closest joint to it. And to be able to understand that, you have to understand what a joint is. So RefNet Y joints are classified as a joint, header is a joint, a multi-port branch selector box is a joint. But the one thing people occasionally get tripped up on is single port branch selector box is not considered a joint. So technically you need more than 130 feet, or I'm sorry, less than 130 feet between a single port box and an indoor unit to follow the rules. So just touching on WebExpress real quick. So when you check that box that I'm showing in that WebExpress snippet, you can go in and enter in every piping length in the system. And you're going to need that for the final design, right? But you can put together a preliminary design with just some overall key lengths that I'm showing here. And really the two key lengths are going to be the equivalent piping length between the outer unit and furthest indoor unit, and the vertical separation between the outer unit and indoor unit. Those are going to be the two factors that are used to determine what the piping capacity correction factor is. So entering those in a preliminary design will allow you to also account for that correction factor. You can also enter in first branch nearest, first branch the farthest indoor unit, and then the separation between indoor units. Now, I mentioned those footnotes and those additional constraints. A lot of those apply to the extended height constraints. So I'm going through each one of those here. So I've separated heat pump and heat recovery. And you see pretty much all of these, to go beyond that standard length, there's a field setting associated with that. The field settings are going to adjust operation just a bit to mitigate some of the effects we see in the system from those static gains and losses. So when the outer unit is below the indoor unit, in heating operation, that field setting is going to increase the target condensing temperature a bit. And then when the outer unit is above the indoor units, in cooling operation, it's going to adjust the position of that EEV in the outer unit. Typically, in cooling operation, that EEV is still open, but it's going to adjust it a bit just to mitigate some of those effects. So there's a field setting across the board for all of these. On a heat pump system, there's an upsize of the main pipe. I'll talk a little bit more about that here in a second. And then really the only other one that has additional constraints is going to be when the outer unit is below the inner unit for a heat pump system. So you see there's a minimum connection ratio increase for this scenario. And it's important to note because the standard minimum connection ratio is 50%, and it could be as high as 110% when you exceed 130 feet, depending on what your equivalent length is in the system. Now, the last one I'll mention is the height difference between indoor units. So standard, that's 49. We can go up to 98, provided we're below 390 feet. Equivalent length between outer unit and furthest indoor unit. That's at L2 plus L3 length. There is a field setting associated with going to 98 when we're exceeding 390 equivalent length. That field setting is like a super secret field setting, not in the manuals. I'm not sure exactly why it's not in there, but that is available. You could reach out if you have that particular type of application. But essentially, beyond within that range, exceeding 390 and having a vertical separation beyond 49 feet, there's noise concerns that we want to make sure people are aware of before they allow that in their design. Now moving on to pipe upsizing. So there's some scenarios where we require an upsizing in a VRV system, and that tends to be when we have longer line sets and we're trying to mitigate some of the pressure drop associated with those longer line sets. There's really three main reasons. So the first one I'll go through, or three main scenarios. The first one I'll go through is the outer unit to furthest indoor unit equivalent length. Whenever that is greater than 295 feet, the main pipe is going to be upsized. So heat recovery systems, whenever you have an upsize, it tends to be just the liquid line, and heat pump will be the liquid line and suction line. So the main pipe is upsized in that case. Remember, the main pipe is that L2, that length specified as L2 between the outer unit and the first rep net. Mentioned earlier, when we exceed those standard lengths for the vertical separation, we have the field setting, and we also have to upsize that main pipe. And that applies to heat pump only. We'd upsize the suction and the liquid. And then the last one is the first rep net to furthest indoor unit. So we have to upsize all the intermediate pipes. Once again, an intermediate pipe is anything that's not directly connected to an indoor unit. So we have to upsize those intermediate pipes. And then there's also a few other additional constraints that I'll go through here in a second that apply to exceeding that 130 feet. Before I do that, I just want to make note of a requirement of never double upsizing a pipe in a system. And that's really really only a concern when you may have a scenario where you have a 7/8 inch pipe. It requires an upsizing, and the next larger size pipe is 1 inch. And 1 inch isn't available here in North America as a copper tube type size. So what is not allowed is double upsizing the 7/8 to a 1 1/8. That would be a double upsize. You would have to keep that pipe at 7/8 inch because that is a favorable situation versus having too large of a line set that's two sizes too large. Like we saw earlier, there's reliability concerns as far as oil return and protecting that compressor with having too large of a pipe versus the alternative of just having too small of a pipe. Will pay a little penalty as far as performance, but it's much more favorable situation than this scenario where we could impact the longevity of the compressor. Now, there's really 4 constraints that apply with exceeding 130 feet from the first rep net. We've already kind of gone through the first 3, so upsize intermediate pipes between that indoor unit and the first rep net. And all those pipes that are upsized will count as double. And then we also went through this one as well. Any indoor unit and the closest branch to it has to be less than 130 feet. The fourth one is the real complicated one. I'm not going to even read it just because it's not going to do you any favors. It's much easier to visualize because it's a difference between 2 differences. So what we're doing is we're taking the difference between A and difference between B, and that has to be under 130 feet. So B is the distance between the closest indoor unit and outer unit. A is the farthest indoor unit and the outer unit. And we're taking the difference between those. It has to be under 130 feet. And that rule is really in place for balancing purposes, right? The closest indoor unit is going to have not a whole lot of resistance to it, versus the farthest indoor unit is going to have a lot of resistance to it with all that additional piping. So we want to avoid scenarios where we're getting too much refrigerant at the closest indoor unit, but not enough refrigerant at the farthest indoor unit. We have some play, right, because we have modulating valves, the electronic expansion valves on each indoor unit, but we don't want to get into a scenario where we're exceeding the controllability of those valves, where we have the valve full open and we're still not getting enough refrigerant to that unit farthest out of the system. So that's why that rule's in place. That's applicable to all air-cooled systems. And really the main reason why I'm going through this in detail, this particular rule, is because on the new water-cooled systems, that complicated last rule is eliminated. So we can actually exceed 130 feet between that distance A and that distance B, and still be within the requirements of the system. Now you may ask, well, how are we doing that and getting that balance that I just went through the trouble of explaining? We have an additional rule that is applied. So any indoor unit that's greater than 4 tons, so 4 tons and greater, we're going to upsize the pipe that's immediately off of that indoor unit. So that's going to allow us to reduce some of the resistance to those larger units that are farther out the system that require a little more refrigerant. So we can reduce that resistance and mitigate some of those balancing concerns from exceeding that length. So keep in mind that does increase the flexibility on the piping side for water-cooled systems quite a bit. And then I just want to emphasize all these are included in WebExpress, so if anybody is feeling a little overwhelmed right now, I just want to make sure you take a breath and remember that all this is included in WebExpress. Like I mentioned earlier, it can be beneficial to know when we need to make corrections to the system, but by no means do we need to memorize anything. And then lastly, I want to go over optimized layouts. So unfortunately, WebExpress defaults to what we don't recommend, which is called a linear pipe route, where essentially everything's in series. You have one long loop, and indoor units are keeping added in series onto that loop. Ideally, you want to do more of a branch type layout, where it looks more like a tree. It's good for a few different reasons. One, from an install cost. You'll see on the left-hand side, we have more larger pipe, so we have 70 feet of 1.125". On the right-hand side, in that branch pipe layout, we have 32 feet of 1.125". So you see a majority of the piping is in the smaller size range for the branch piping, and the majority of the piping is in a larger size range for the linear pipe route. So it's the same system, same size system. All we did was change the how the piping connects all the units, and we're able to not only reduce the cost of the piping, but also reduce the refrigerant charge of the system, which has a cost impact as well as a code compliance impact with ASHRAE 15. And then also the system on the left is going to be more inclined to exceed that differential rule we just went through. So the air-cooled systems still have that rule in place. And doing a linear pipe route, you're going to be much more inclined to have a large distance between the closest indoor unit and the farthest indoor unit. Alrighty, so moving on to oil traps. Generally speaking, no oil traps are required in a VRV system. And that's because we have advanced oil return techniques and we're properly sizing our pipe, so we don't need oil traps, traditional suction riser oil traps or inverted traps out in the system. And how the oil return cycle works is essentially when you first start up the system, within 2 hours, it will go through oil return cycle, and then typically every 8 hours after that. Ultimately, it's going to be based off of the cumulative oil feed rate, which is based off of the parameters that I have listed there. So 8 hours will give you a rough idea. And it lasts anywhere from 3 to 12 minutes, and that depends on compressor frequency and suction pipe temperature. As far as what is actually going on in the system is essentially going into cooling mode, ramping up the compressor, opening up the expansion valves to get the velocity up in the system and the oil back to the compressor. And what people tend to be more concerned with is what's going on in the indoor units, especially for any indoor unit that may be in heating mode. So I've listed what's going on with the fan, what's going on with the EEV to give you an idea. Generally, the fan is forced off when we're going through this oil return cycle if the unit's in heating mode. And then the EEV might be opened up to the minimum position, or in some cases, in a thermal on condition, it's going to be opened up all the way. Now, as far as oil traps out in the system, so the main concern is going to be that primary loop. that I have highlighted in light blue there. So for when the operator is below and when the operator is above, what we're trying to avoid is multiple direction changes. So essentially you can do one direction change where you're coming out of the operator, going up, going over, and then coming back down and hitting the end arenas. What you can't do is go up, come back down, and go up again, because that would be classified as a pipe. That same concept applies to, or as a trap. So that same concept applies when operator's below, operator's above. As far as the actual branches on the end arena branch offs, we allow 3.3 feet of vertical separation. And that's primarily to allow for piping to go around like structural beams or things that you just possibly can't get around. Doesn't mean you should make the piping look like a wave getting to the end arena. Obviously, we want it as least amount of resistance to that unit, least amount of pressure drop from a performance perspective. So when you're doing that 3.3 foot turn to get around something, you want to try and make it as smooth as possible. So long radius bends. If it's hard copper and you're using joints, then try and use 45 joints like you see in the recommended layout on the top there, rather than 90s. Now, I said generally there's no oil traps, and I said generally because there are times where we need inverted vertical oil traps between the operators. So there's really two cases where that's going to happen. And this applies to both air-cooled and water-cooled. A lot of times the second case there is just talked about in water-cooled just because it's more likely that the refrigerant connections are going to be coming in from the top. But in that second case, anytime where we have refrigerant lines coming in from the top and going into the refrigerant connections on the unit, we need inverted vertical traps, air-cooled or water-cooled. And then anytime we have greater than 6.5 feet between ref nets or out-the-unit multi-connection kits, or greater than 6.5 feet between a connection kit and an out-the-unit, that's when we're going to need an additional 8-inch inverted vertical trap. And ultimately, what those traps are trying to do is prevent oil from accumulating in an out-the-unit that's in standby or that inactive line set up to that unit. All right, so now we'll move over to thermal expansion and insulation. Now, before we do that, I mentioned these are both kind of related because they both have to do with the refrigerant piping temperatures. So we first need to get an idea of what the typical temperature ranges in the piping system we're going to see are. And to do that, I'm going to use a pressure enthalpy chart. So I just kind of want to briefly review exactly what that is. So here in the dark blue line, you see just the typical vapor compression cycle, so a heat pump cycle. So you can really determine what the temperatures are in the system for any heat pump cycle, whether it's a mini split, VRV, multi-split. If it's a vapor compression cycle, you can plot it on a pH chart and get an idea of what the temperatures are going to be in the system. So it's really no secret. It's just a nature of the refrigerant cycle. So the main things we're going to be looking at is the constant property line for temperature and entropy. So temperature are those green lines off to the left side in the subcooled region. As we go to the left, the temperature will decrease, but the pressure will stay constant. Within that dome, that vapor dome 4R410A, it's a constant temperature, constant pressure process. And then on the right-hand side, that's a constant pressure, but as we go to the right, we're going to increase in temperature because we're superheating that refrigerant. And then the last thing I want to mention is the entropy lines. So those are those light gray lines in the superheated vapor region on the right-hand side of that plot. So those are basically, when you compress a refrigerant, it's a constant entropy process. So it has to follow that line, has to follow the slope of that line. In reality, you'll pick up a little bit more heat just because of the inefficiencies of the compressor, but you have to at least pick up that amount of heat. So you compress a refrigerant from one pressure to a next, there's a fixed amount of heat that you have to pick up. And in reality, accounting for inefficiencies, you pick up a little bit more than that. So looking at the typical cooling cycle, first we got to figure out where the liquid line falls on that plot we're just looking at, the pH chart. So liquid line, liquid's going to be coming out of the outdrainant. So it's going through the indrainant, or going through the heat exchanger in the outdrainant, getting a little subcooled, and then there's an additional subcooling circuit that's applied, and then that subcooled liquid is sent from the outdrainant to the indrainant. Now that subcooled liquid is going to fall in the top left corner of that cycle that we see on the chart there. And you see two cycles I plotted there. One's for a high ambient cooling condition, one's for a low ambient cooling condition. So you can see the temperature of that liquid is going to vary a little bit based off of the ambient condition. So it's going to be around 70 to 110 degrees, generally speaking. 70 to 110 degrees is what you can expect for a liquid line. And then with in cooling operation in a heat pump, we're maintaining the suction temperature or the evaporation temperature. And typical target's 43 degrees, and we typically try and go for 9 degrees superheat. So you're looking at around 52 degree suction temperature going from the indrainant to the outdrainant. So suction pipe around 52, liquid line 70 to 110. Depends on operation conditions, but that gives you a rough idea of what to expect. The suction line will never go below 32 degrees because there's protection measures, indrainant freeze protection control in place that will try and counteract that. As far as heating, we're going to see similar temperature ranges for heating for the liquid line. It's a little bit different because the liquid is now coming from the indrainant and going through the outdrainant where it's subcooled and then expanded and then evaporated. But that it's going to be a little more consistent just because in heating we're maintaining a set condensing temperature. So you're looking around 100 to 110 degree Fahrenheit. Liquid line, gas line, this is where you're going to see the hottest temperatures in the system just because of that process I mentioned earlier. We're picking up all that heat in the compression process. Nothing we can do about it unless we're using some sort of like vapor injection type of mechanism. But when you're compressing a refrigerant from one pressure to another, you pick up a set amount of heat, and you can see that heat or that discharge gas that comes from the compressor goes directly to the indrainant. So we see that hot point in the system on the top right-hand corner in the suction line in heating mode. So you'll see your hottest temperatures in the system in that suction line in the lowest ambient conditions. So again, I plotted two different scenarios here. You see the one with the smaller difference is a low ambient heating condition, or I'm sorry, a warmer heating condition, and then the larger one is a low ambient heating condition. So the lower that suction temperature gets, the more heat you pick up. So you're going to see your hottest temperatures and your coldest times of the year when the unit's heating. So now we have a rough idea of what the temperatures are going to be, the temperature ranges are going to be in the system, so we can kind of apply those to accounting for thermal expansion and contraction. So anytime a pipe is fixed on both ends, you have to provide some provisions for that pipe to move because it's going to expand and contract as the temperature changes in that. There's a number of different ways you can do that. A simple change of direction is going to allow for that change. You see that red arrow there. Basically, you have a deflection mechanism. Is that vertical pipe, provided you have a guide there. A simple offset, sometimes called a Z-bend, is also a method to account for thermal expansion. And then the more commonly known expansion loops are a method to account for thermal expansion. So there may be scenarios where you don't even need an expansion loop. You might just have enough direction changes or offsets within just the standard piping layout, just how it's laid out. That's something you have to determine. But there may be scenarios where you need to add an additional expansion loop. So you see each one of these have a length that's specified as L. Is basically the length of the deflection mechanism that's needed to avoid putting too much stress on the pipe. So it allows the pipe to move if you maintain that length without putting too much stress and damaging the pipe. Because we want to avoid scenarios like we see in the top right-hand corner where they didn't have enough length and they're pinching off pipe. You could run into scenarios where pipe could rupture, things like that. Oh, and one last thing I want to mention on those expansion loops. It's really important that those are installed in the horizontal plane because if you install them in the vertical plane, that's a vertical track, right? like we talked about earlier. We want to try and avoid those traps in those throughout the system. So how do we determine what that length L is, that deflection mechanism length? So to do that, you have to first determine what the expected thermal expansion is. You can do that with the formula I'm showing there, which is a function of the length of the pipe, the temperature difference. So the temperature difference, it's important to note, is the difference between the ambient temperature that it was installed at, so the temperature when you installed it, and then either the hottest or the coldest, whatever results in the biggest difference. Typically, it's going to be the hotter end, the expansion. That's going to be the bigger difference, and you use that to account for thermal expansion. And then obviously the thermal expansion coefficient of copper, that's just a fixed constant value that you plug into that equation there. So what I did was I just laid out a rule of thumb. You could say you could have an expected thermal expansion of 1.73 inches per 100 feet, assuming some worst case scenarios, 220 degrees outside, 65 degree install temperature, and that will give you a good conservative value to put together some expansion estimates. Now keep in mind that 220 is specific to that low ambient heating condition. So then once you determine your expected expansion, you would use that along with the size of your pipe and apply it to that chart that's on the right-hand corner. So that's taken from the Copper Tube Handbook, and that's going to tell you what that distance L is going to be, or what that radius R needs to be to provide enough expansion movement in that loop. So I just want to go through a few examples of that. So using a change of direction, we could assume we have a piping segment that's 100 feet between two fixed points. So between the fixed ref net and that fixed blue square that I'm showing there. So that's 100 feet of half-inch suction line. Using that rule of thumb that I mentioned earlier, that 1.73 inches per 100 feet, that would give you, using the chart in the bottom right-hand corner there, rounding up to 2 inches, we had half-inch suction line. The L distance would need to be 99 inches in that case. So if we had a guide, we would need 99 inches between that joint and the guide. If we didn't have a guide, we would need the 99 inches between the joint and that fixed point. Now, what would happen if you didn't have enough, if L was not long enough with just a direction change? What you need to do is add an expansion loop in that 100-foot section. So you could do something like I'm showing on the right-hand side there. Very similar distance. The L distance is the same, and you calculate it in the same manner using that chart. In this case, very important that that expansion loop is installed in the horizontal plane. And then one last example, looking at a vertical riser offset example. So with a vertical riser, looking at the scenario we have with a fixed support in the center and then some guides on the top and the bottom, you're going to get some room for expansion just from the direction change that you see on the top and the bottom. But if for some reason that's not enough, you could add a Z-bend or an offset to account for that additional thermal expansion. That's what I've gone through here. So we saw that L for an offset or a Z-bend is going to be 65% of the L that's used for like a direction change or an expansion loop. So what I did was we had a 100-foot section of 3/4 inch copper tubing. I used that rule of thumb I had earlier, that 1.73 for 100 feet. So I rounded up to 2, 3/4 inch line, 117, and that's 65% of that is 76 inches. So that gives you an idea of what that deflection mechanism needs to be. Now moving on to insulation. So I'm sure a lot of people are familiar with this table. This is from the IECC International, I forget exactly what it stands for, the main construction code. It basically dictates what thickness insulation you need based off of the fluid operating temperature. So it's kind of a gray area as far as what we're using for that fluid operating temperature, which could play a big part of the thickness. There could be a big difference in the thickness that we need depending on what temperature we're using. So do we use the rated condition refrigerant temperatures? So that's going to be what we're seeing in the bottom left hand there. So 140, So we'd be looking at an 1.5 inch insulation, which is a little reasonable. We look at the estimated max refrigerant temperatures because we know those aren't going to be applicable to all climates, right? So 220, that's really an extreme condition if maybe you're operating the unit at -13 degrees outside and it's in heating mode. So for a 3-pipe VRF system, your max is going to be around 220. 2-pipe, it's going to be around 190 degrees. And those are just generic properties of a heat pump system. So it's not anything we can really get around unless we have another enhancement like vapor injection that can counteract that a bit. Or do we use the VRF protection limit, which is 248? So overall, typically what's being used is the rated refrigerant temperatures to determine what the insulation thickness is, but ultimately it's what your authority having jurisdiction requires. And I've seen some areas where they enforce some things and some areas where they enforce others. Really comes down to them when it comes down to it. But just to give you an idea of the different temperature ranges and the associated thicknesses. Ultimately, at the end of the day, what we're trying to do with insulation is conserve energy, right? But we want to do that in an economical manner. We don't want to put a ridiculous amount of insulation on there to conserve as much energy as we possibly can if it's mitigated entirely by how much it costs. So what I've done is I've actually included some information from a peer-reviewed journal paper that does exactly that. It looks at the economic optimum insulation thickness for VRF systems. So what they determine these thicknesses here, and you can see they're far less than what we see in that IECC table. And this is for optimal performance, balancing cost and energy savings. It is a peer-reviewed journal article. I listed the conditions there. The conditions are not exactly what you'd see in our VRF system, but it does give you an idea that the insulation thicknesses, if you're really looking at the whole picture, really it's in our favor to have them. It's not in our favor to have 2.5 inch insulation on a inch diameter suction line. So overall, the type of piping that we need in the system is going to be ACR copper tubing, soft or hard. It's really going to be determined by the installer. We saw that size is important. The main thing that critical for sizing is the reliability concerns, right? We want to try and protect that compressor. There's also performance concerns. There's also cost concerns as well. We went through all the different length constraints. Fortunately, all those are applied for us in the selection software. They can be useful to know, so we can, when we're exceeding those for some reason, we can know what we need to do to correct that system. Branch layouts are going to be the best route to go. Branch layouts are not the default in WebExpress, so it does take some work to rework that system, but it's going to allow you to decrease the install cost and get a better balanced system. We saw overall oil traps aren't required in the system, except when we're talking about between modules on a multi-module system, and that applies to air-cooled and water-cooled. And then we just finished looking at the temperature in the refrigerant piping network and how that affects insulation and thermal expansion. And there's really a number of different ways to account for thermal expansion, but it's something we need to make sure we do so we're not running into scenarios where we're cracking pipe or pinching off pipe. So that finishes everything up for me. This time I'll open up for questions.
Okay, let me go ahead and look at the questions. We said we have one that says, "You sure we can have a connection kit FP, excuse me, above outdoor cool system?"
Yeah, so the air-cooled system, if you look in the air-cooled installation manual, you'll see that you can have the connection kit above the outdoor unit. If you want, you can shoot an email to applicationsengineering@daikincomfort.com, shown on the screen here, and I can direct you to exactly where that is in the install manual.
Okay. All right. And there's another one that says, what's the normal operating temperature for the superheat?
I guess I don't know exactly what you're asking. I mean, that could be a number of things. Maybe you can explain a little bit more what the intention of the question was, and shoot us an email, and I can get back to you on that one.
Okay, let me go ahead and continue. Hi, this is George Hernandez from Daikin, Mexico. Is it possible to get this presentation to training for training purposes?
Yeah, I can share the presentation. We can talk about that. Again, I'll refer you to that email there. We'll see exactly what you're looking for, and we can share the presentation or set it up. Whatever you need, we can figure something out.
Okay, and George also said one question: is it recommended to apply heat to bend or expand the copper pipe?
That I wouldn't be in a position to comment on. I would refer you to the service team. They might know that, but that's something I would reach out to, like a contractor or installer. They're going to be much better suited to answer that type of question.
Okay. You have a couple more. Why is the indoor to indoor distance cut in half for the new VRV X unit?
So that's not anything new to the new VRV X unit. So that's always been the case for heat recovery systems. We can go up to 98 feet as long as you're within 390 feet on the equivalent length. When you're between that 390 to 540 range, there's a concern for noise. We can go beyond that, but there is a field setting that you need to apply, and you have to reach out for that field setting.
Okay. You have a couple more. Where do we confirm the long Linus field setting? So long line set field setting. Where do we confirm the long line set field setting?
So all the field settings I went through, those are the best source for field settings is in the service manual. So the only field setting that I didn't provide was that field setting for the rule we were just talking about. On heat recovery systems, when you have a vertical separation greater than 49 or 48 or whatever it is between indoor units.
Okay. Someone else asked, is the presentation available online?
Yep, yeah, so there's going to be a YouTube link that's sent out for the presentation, and then I'm also going to post the presentation up on Daikin City within the next day or so.
Okay. Someone said, hello, I may have missed this slide, but is the distance between the ODU that would dictate whether or not a P trap is needed?
Yeah, I guess I don't know what the question's asking. Maybe you could send me an email and we can kind of figure out what you're trying to determine there and go from there.
Yeah, that's from Tiffany. Tiffany, send him an email and he'll be able to answer that more. Answer 918 superheat degrees depending on the delta temperature of return air and set point, I believe. That's what Jordan Cummings said.
Oh, okay. Back to that superheat question. Yeah, so superheat at the indoor unit, yeah, the typical target is always going to be anywhere 9 to 18 degrees. I think on my slide I listed 9 degrees, but that can fluctuate, right?
And Tiffany was saying ODU to ODU, manifolded ODUs. So she retypes back in there, just basically saying the ODU to ODUs, manifold ODUs. So maybe she could email you to be more specific.
Yeah.
Okay. Robert Powell said, why does the 130-foot differential apply to water cooled only?
30-foot differential. Oh, so then that new rule for the water cooled. That's just because it's one of the newer products. I think there may be a time where that gets applied to everything, but the water cooled is one of the newer products. I couldn't tell you exactly why they decided to give us the flexibility on the water cooled and not the other units, but I guess it's a newer unit. Maybe they're testing out this rule on the water cooled, and it could be applied eventually to the other products.
Okay. Joel said, do we have details on how to support the vertical rises for 250 plus length to still account for the expansion?
Yeah, so you can see kind of the some of the stipulations for supporting a vertical riser in there as far as where to use a guide versus a fixed. I didn't include any like distances between those and all that sort of stuff. I was trying to lean more towards the application side rather than the install guide. But I'm sure in the VRV install and commissioning course, they go through distances between supports of piping and all that sort of stuff. So if that's what you're looking for, I'd recommend looking up those presentations and getting that information there.
Okay. Someone said, is there any published literature regarding the use of REFLOK, REFLOK, or Zoom lock with Daikin VRV?
Yeah, so that's kind of a sensitive topic right now. We don't allow it. It's not to say it's always going to be that case, but right now we have to say follow the install manual, which refers to brazing and flared fittings. Yeah, this is how it is currently. May change at some point in time, but we're currently not in the position to be supporting Zoom lock or REFLOK or anything like that.
Okay. And the last question is the pipe length from a multi-BS to fan coil limited to 65 inches, not 130 when utilizing two ports greater than 54K?
Yep, yeah, you're spot on there. I think I added a little footnote on one of the slides, but I forgot to call it out. So whenever you're twinning a port, that distance between the port and the indoor unit has to be 65 feet versus the standard 130 feet. But yeah, good point. Forgot to call it out.
And Rusty Hoffman said, I would like to get a copy of this for internal use. Rusty at hoffmanandhoffman.com.
Okay. Yeah, not a problem. We'll have this up on Daikin City within the next few days here.
Cool. Well, that concludes all the questions and everything. You did a fabulous job because you had a lot of questions. Do you want anything in closing?
No, I'll just thank everybody for their time. I added a little note. If you guys had any suggestions as far as what topics you'd like to see for webinars in the future, feel free to shoot that over to myself for the applications engineering folder, and we can look into putting something together if we think it's going to be valuable. But thank you.
All right, that concludes our webinar today. As always, we appreciate everyone's participation, and have a wonderful day.